Hello and welcome to this A-level chemistry explanation video where we're going to be taking a look at NMR spectroscopy. This is the instrumental technique that's used to analyse organic molecules, and it's actually the same technique that is used in MRI scans in diagnostic medicine. The video will focus on how this NMR spectrum is generated, but also how we can build together the different parts of a puzzle that we can use to identify an unknown substance as a result of our analysis. There are two types of NMR spectroscopy that you need to know about. There is carbon-13 NMR, and that tells you how the carbon atoms in a molecule are arranged. And there is also proton NMR or hydrogen-1 NMR, and that tells you how the hydrogen atoms in the molecule are arranged. There are other types of NMR that you don't need to know about for A-level chemistry, but what those types have in common with carbon-13 and proton NMR is that the nuclei under investigation have got an odd number of nucleons. That means an odd number of protons and neutrons in their nucleus, and this gives rise to a property called spin. The nuclei of carbon-13 and hydrogen-1 have spin, and that means that they have some interactions with magnetic fields that we're going to explore. Within those two, there are four different sort of rules for NMR spectroscopy that you need to know. And two of them are common to both those two types of NMR, and that is to do with the different environments within the molecule, and that's the first rule that we'll take a look at. And then the second rule is to do with something called chemical shift. And then there are a further two rules that only apply to proton NMR, and these rules are referred to as the integration trace, which is to do with the area of the peak, and then the splitting pattern, which is to do with the precise shape of the peak. NMR stands for Nuclear Magnetic Resonance Spectroscopy, and that is an incredibly descriptive name because what we're doing is we're looking at the nuclei of atoms within a molecule and seeing how they resonate when an external magnetic field is applied to them. And the effect of that is energy is given out by the molecule and it is detected in the NMR machine, and the type of energy or the frequency of the energy that is detected corresponds to a particular arrangement of atoms within the molecule. And that's because nuclei in different environments absorb different frequencies of energy. And these absorptions give us clues about how the atoms are arranged. The number of peaks that you see in a particular spectrum tells us how many non-equivalent environments there are for protons or for carbon atoms, because each different arrangement will correspond to a different absorption of energy by the nuclei and a different frequency of energy released. And so what this looks like in practice is that if you have an NMR spectrum with only one peak, that means that all of the carbon or all of the hydrogen within a particular molecule are in the same environment. And so if we take something such as ethane, you can see that what we've got on the left of the chain is a CH3 connected to another CH3. On the other end of the chain, we've got the exact same situation. So this will only have one peak in either the proton or the carbon-13 environment. If we then moved on to look at propane, you can see that we've got the environment for carbon atoms, which is we've got a carbon with two hydrogen, that's the one in the middle, and then we've got carbons that are part of CH3s and are on the end of the chain, and those are equivalent. So this propane molecule would have two different environments, and so therefore two different peaks in the carbon-13 NMR spectrum. And this is the same for hydrogen as well. If we take a look now at ethanol, and first of all consider the carbon atoms in ethanol, there are two carbon atoms, so the maximum number of environments that we could have is 2, and we can see that both of these carbon atoms are different. We've got a CH3 and we've got a CH2, so they have definitely got a different environment, and so there would be two peaks in the carbon-13 NMR spectrum. Then if we look at hydrogen atoms, we've got hydrogen atoms on the CH3, which are going to be different to hydrogen atoms on the CH2. And then we've got this third hydrogen, which is attached to the oxygen. So that's a third type of environment. So if we looked at a proton NMR for ethanol, there would be 3 peaks, whereas in carbon-13 NMR, there would only be 2. The last thing to say by way of an introduction to this idea is, what do I mean by non-equivalent hydrogen environments or carbon environments? Well, the best way to illustrate this is if we look at butane. You can see that in butane, we've got 4 carbon atoms, so we could have 4 peaks in the carbon-13 NMR. But we have got 2 equivalent environments. We've got the CH2s in the middle, and they are equivalent to each other. And we've got the 2 CH3s at the end, which are equivalent to each other. And so because they are equivalent, they would both give the same peak in the carbon-13 spectrum and in the proton NMR spectrum. And so we would only see 2 peaks for butane. Some people like to explain this as if each of the environments is placed in a house and the neighbouring environments are like atoms living in the house next door. And so environments can be considered to be equivalent if they have the same next door neighbour and the same neighbours living 2 houses along and 3 houses, etc. A quick way of looking at this is to look for symmetry. There is a line of symmetry, and it's particularly obvious how we draw it in 2 dimensions like this, and you can see that there's a line of symmetry down the middle, and then for all intents and purposes, we can actually pretend that the other half of this molecule doesn't exist from the point of view of working out how many different environments there are. When it's got some lines of symmetry, there is usually fewer peaks than you might expect. The number of peaks in NMR spectroscopy is down to the number of non-equivalent environments for either carbon or for hydrogen. So if we look at 3 examples of this that are all based around an aromatic compound, if we start with carbon-13, what we're working with here is benzene, and benzene is C6H6. And so each of these vertices is a carbon atom, and each of those has a hydrogen atom attached to them. And this circle represents the pi cloud of the benzene ring. And what this means is, in the carbon-13 NMR spectrum, there will be only 1 peak, because every single one of these environments will be the same. And so there is only 1 environment, 1 set of equivalent carbon atoms. And it will be the same for proton NMR as well, because each of these carbon atoms has got a hydrogen atom attached to it, and so they will all be equivalent, and so there will be 1 peak. This simplicity changes when there are some branches on our benzene ring, and we can see that in our second situation. First of all, if we take a look at the carbon NMR, there is obviously this carbon atom that has got the chlorine attached to it. And so that's a unique environment. There is 1 carbon with 1 chlorine attached to it. And as we work our way around, we encounter 5 carbons with 1 hydrogen attached to them. And so we could be forgiven for thinking that they were all the same. But this carbon has 1 hydrogen and is 1 bond away from the carbon with the chlorine atom. And the next carbon around the ring is 2 bonds away from the carbon with the chlorine. So even though these are both CH groups, they will not be equivalent to each other. And in the same way, this carbon here is a CH, and it's going to be 3 bonds away from this carbon with the chlorine. And so what we're going to end up with is 4 different environments for carbon atoms in this substance. We have got this one, and then we've got this one, and then this one, and then this one. And we can get faster at this because there is actually a line of symmetry through this molecule at this diagonal like so. And what that means is anything that falls on the line is likely to be unique, but anything that is equivalent position either side of the line is going to be an equivalent environment. And so that's why we've got 2 identical environments here and a second identical environment here. And so there would be 4 peaks in the carbon NMR. The proton NMR would follow the exact same rules because that line of symmetry is still there, but because this carbon atom here doesn't have a proton attached to it, this would not be an environment in the proton NMR because there isn't a hydrogen atom there. But the other three environments would still be there, and for the exact same reasons, there would be three environments in the proton NMR spectrum. If we take a look at the bottom one, we have actually got 7 carbon atoms here, and so we could have as many as 7 peaks in the carbon-13 NMR. However, there is a line of symmetry straight down the middle, and so the CH3 falls on that line, so that will be unique. Then there's the carbon atom here with nothing attached to it that is kind of hidden, there's no hydrogen attached to it. And then as we work our way outwards, both of these two environments are going to be the same. There's a carbon with a nitro group attached to it. And then as we work our way downwards, here is a carbon with a hydrogen attached to it. And then last of all, another carbon with another nitro group attached to it. And so you might think that these nitro-containing carbon atoms will all be equivalent, but this one at the bottom is a long way away from this methyl-containing carbon, and so it will be a different environment to the carbon with the nitro group just one bond away. So this line of symmetry tells us that there are in fact going to be 1, 2, 3, 4, 5 environments for carbon in this molecule. For hydrogen, it will be simpler, in fact, because there are these hydrogens here on this methyl group. That's a unique environment. But in fact, there isn't a hydrogen atom here, or here, or here. There is, in fact, just this last position where hydrogen atoms can be found. So there are, in fact, just 2 environments in the proton NMR spectrum, so 2 peaks. When you analyse a sample using NMR spectroscopy, the substance that you're analysing needs to be dissolved to make a solution that can fit inside the glass testing tube. When you are selecting your solvent, there are 2 really important choices that you have to make. First of all, your solvent must not interfere with the spectrum that you're hoping to create. So really what this means is it shouldn't contain any protons, because if it did, they would also add to the spectrum being produced, and you wouldn't know if they were coming from the solvent or from the sample that you were trying to analyse. And then secondly, and this is perhaps somewhat obvious, it needs to actually dissolve the sample that you're hoping to test. And there are 2 types of sample that you might be analysing. You might be dissolving a polar substance, or you might be dissolving a non-polar substance. And each of these different types of substance requires a different type of solvent. There is a truism in chemistry, which is that like dissolves like. And the reason for that is that if you have a polar substance, it will need to dissolve in a polar solvent because that is the type of substance that it can interact with. It will be attracted to it. And similarly, a non-polar substance will need to be dissolved in a non-polar solvent. There are 2 examples that you need to know. Non-polar solvents, we've got tetrachloromethane, and polar solvents, we have got CdCl3. So if we take tetrachloromethane first, we can see that we've got carbon bonded to chlorine, and that should be a polar bond, but because we've got this tetrahedral arrangement of the 4 chlorines around the central carbon, they are going to cancel each other out, and there will be no dipole moment in this substance, so it will be non-polar. CdCl3 is different. It will be polar because we've got 3 chlorines in one area of this molecule, and we've got this atom that we're labelling as a capital D. Now what that is heavy hydrogen. This is hydrogen that's got 1 neutron. So instead of it having a mass number of 1 for the 1 proton it's got a mass number of 2. And so that means that this atom has got an even number of nucleons, and so it does not possess the property of spin, and so it will not interfere with the spectrum. And not only that, we've got the 3 chlorine atoms that are pulling the electrons in one direction, creating a region of polarity with the slightly electron-rich region, and we've got the hydrogen, which is not doing that, and so this molecule will have an uneven distribution of electrons, and so will therefore be polar. There will be a dipole moment. NMR spectroscopy measures differences in the energy absorbed by nuclei in different environments compared to a standard substance. And this substance is referred to as the chemical shift value and is given the Greek letter D, the delta symbol, and that is usually referred to as a delta value or a chemical shift value. It's measured in parts per million, and that means it's comparing the shift in the energy being produced by the proton or the carbon being measured compared to the standard substance or the reference value. And this standard substance is something called tetramethylsilane, and that's used in both types of NMR spectroscopy. This is the structure of tetramethylsilane. It is a very logical and literal name. The silane comes from the silicon that is the center of this substance, and we have got 4 methyl branches sticking out of it. And what's distinctive about this tetramethylsilane is that even though it's got 12 hydrogen atoms in its structure, they are all identical environments, and the 4 carbon atoms are also all in identical environments. And so that means that for both the proton NMR and the carbon-13 NMR, the tetramethylsilane will only produce one single absorption peak. And a characteristic of this molecule is that the peak for those protons or those carbon atoms will be a long way away from all the other absorption peaks. And that's due to the symmetrical nature of the molecule and the way that the carbon interacts with the silicon. And so this single peak produced by tetramethylsilane is given a value for its chemical shift of 0. And everything else is compared to the chemical shift of this peak. And so you will see sometimes on a spectrum that there is a really small peak for the tetramethylsilane at chemical shift value of 0. And so this is to be ignored. This is for the reference. It is not coming from the sample that is being tested. This is the tetramethylsilane peak. The fact that you only get the one peak from tetramethylsilane and it is a long way away from any of the peaks that you'll get from your sample is probably the greatest reason why we choose it for our reference chemical. But there are a few other reasons that you might be required to state in a test situation. The first of these is the fact that it is an inert chemical. And so what that means is it won't react with the sample and so therefore won't create any confusing peaks or eliminate any peaks that would otherwise be there if a reaction hadn't happened. So that's inert. Another reason it's non-toxic, which means that the people analysing the substance won't be at risk. The last reason is that it is highly volatile, which means that you can remove it from the sample really easily once you've run the NMR spectrum. And so that's a physical reason, whereas the inert nature of the chemical is a chemical reason. The spin of an atom's nucleus, and therefore the energy absorbed when an external magnetic field is applied, depends on what type of atom is nearby within the molecule. And this in turn affects the chemical shift value. In general, the presence of a highly electronegative atom nearby within a molecule is likely to increase the chemical shift of nearby protons or carbon atoms. The good news is you don't have to memorize any chemical shift values. What you need to be able to do is look at a spectrum or some information from a spectrum and work out what groups are present within a molecule based on chemical shift values that you get presented with. And you get a data sheet in exams to help you to work this out normally. You normally find the MR chemical shift data in the same sort of place that you'll find the infrared absorption data on the data sheet. Now there's 2 tables that you need to look at typically because proton NMR has a significantly smaller chemical shift value than carbon-13 NMR. If we just take a look at a few examples of this, if we think about proton NMR, a chemical shift value of 2.1 to 2.6 would indicate the presence of a proton, so a hydrogen atom, on a carbon atom adjacent to a carbonyl group, as I'm showing here. The chemical shift values are shown as a range because the precise values, how far it's shifted away from that TMS at 0, is going to vary from one molecule to another. Another common chemical shift value is for a hydrogen atom on a carbon that is connected to the oxygen of an ester group. So in other words, the oxygen that's being sandwiched between two carbon atoms, and then you've got the carbonyl carbon on the other side. And this is found in the range of 3.7 to 4.1 parts per million. And that's evidence that this proton, this hydrogen, is closer to a number of highly electronegative atoms, so the electrons that it's got are being pulled away by those atoms, and that is leading to a larger chemical shift value. As I said, the chemical shift values for carbon-13 NMR are typically about 10 times larger. If we take a look at the peak for a carbon connected to a carbonyl group, that chemical shift value is likely to be between 20 and 50. And another example would be a carbon atom in a benzene ring, and that has got a chemical shift value of between 110 and 160. And the carbonyl group in an ester or a carboxylic acid will have a carbon that gives a peak at between 160 parts per million and 185 parts per million. So you can see that it is a range, and you can see that they are much bigger for carbon-13 than they are for proton NMR. But the good news is, like I say, you don't have to memorize these numbers, you just have to piece together the different parts of a molecule using chemical shift data that gets presented to you in a test situation. The first rule that only applies to proton NMR spectra is the integration trace, sometimes referred to as the integration value. And this is how the area of a peak in the NMR spectrum is given a ratio, which is to do with integration in maths, but we're not actually going to do any integration. We're just going to be looking at the areas of the peak. Now, these are sometimes just given to you in a test situation as a ratio, or sometimes they are shown on a spectrum themselves as a ratio using just simple integer ratios like I'm showing here. The integration ratio itself shows us the number of hydrogen atoms that are contributing to each peak. So if we take propane as an example, we've already seen that it is going to have two different peaks because of the two non-equivalent hydrogen environments. But if we consider the two CH3 groups at the ends of the chain, those peaks are going to be caused by 6 equivalent hydrogen atoms, whereas the CH2 peak in the middle is going to be caused by just 2 hydrogen atoms. And so that means the integration ratio, or the size of the peaks, or the area of the peaks, will be in the ratio of 6:2, or more simply 3:1. And if we look at another spectrum for something such as ethanol, where we have got 3 non-equivalent hydrogen environments, the ratio of these peaks will be 3 for the CH3 to 2 for the CH2 to 1 for the OH group. So they will be in a ratio of 3:2:1. The way that they complicate this a little bit is if they tell you that there are peaks in a ratio of 0.4 to 1.2 to 2.4. And you have to turn that into a whole number ratio. And so the way that you do that is you divide them all by the smallest, which is 0.4. And so this then gives us a ratio of 1 to 3 to 6. And the even better news is that for an A-level situation, normally the integer ratio of the hydrogen atoms causing each peak should add up to the actual number of hydrogen atoms in the molecule being analysed. Outside of an exam situation, that isn't normally what you would expect to find, but they do try and simplify things a little bit in a test situation. And this might be something that contributes to part of a bigger picture, or it might be the only information you need to decide whether a substance that's being analysed is, say, butan-1-ol or butan-2-ol. Because if we take a look at these two examples, they are both going to give us 5 different peaks in the proton NMR spectrum, because we've got 5 different environments for our hydrogen atoms. But if we take a look at what the integration traces will be for each of these, the top one, butan-1-ol, will be 3 to 2 to 2 to 2 to 1, because that's the number of hydrogen atoms causing each of those peaks that we would see. Whereas in butan-2-ol, it would be 3 to 2 to 1 to 1 to 3. And so we would be able to look at the spectrum for our unknown sample, look at the integration trace that it reports, and we would know which of these two unknowns it was. The final rule for proton NMR spectroscopy is something called the splitting pattern, which you only see in the high-resolution proton NMR. And that is effectively the normal NMR, but zoomed in to get a clearer picture. And the best way to illustrate this is if we take a look at this black dot that is in the middle of the screen here. I've asked the question, how many dots really are there? And so what we're seeing right now is the low resolution picture. If we zoom in, we get a clearer image, we get the high resolution picture, and you can see that there are, in fact, 5 dots present here. In high-resolution NMR, we are of course not looking at dots, we are looking at peaks. These peaks might be drawn as single lines, or they might be drawn as triangular spikes. But what we do know is in the high-resolution NMR, they don't all look the same. There are 5 different types of peak that you could encounter, and they each have a slightly different name. And so if we take a low resolution image, which might look like the triangular peak, like so, if we zoom into a high resolution for each of these lines, they might end up looking different. And so we might see what's called a singlet, which is where we get a single line or a single spike. The next possibility is a doublet, which is 2 lines, or a spike that has been split into 2, or a triplet, which is 3 lines, or a triangle spike cut into 3, a quartet, which is 4, or 4 little mini peaks, and the last option is a multiplet, which you're never going to be asked to draw, but that is basically 5 or more. It's a sort of catch-all phrase that includes anything greater than 4 peaks. Now, in order to determine what you would actually see for any given peak when you look at it under the high-resolution mass spectroscopy, you need to understand what is referred to sometimes as the N+1 rule, where N is the number of non-equivalent protons on adjacent carbon atoms. To explain this, it's important to remember that the property of spin that these hydrogen atoms have got means that they behave like mini magnets, and they interact with the magnetic field, as I've said before, and that's how we actually see a peak forming at all. But these non-equivalent protons, they actually affect each other, just in the same way that conventional magnets would interact with other conventional magnets. And so every time one of these protons interacts with another non-equivalent proton, the peak splits from the simple single triangle into either a doublet, a triplet, etc. And so it splits once for each of these non-equivalent protons on adjacent carbon atoms. And so if there are no protons on the adjacent carbon atoms, this will be a true singlet, which will look like this. If there was one hydrogen on an adjacent carbon atom, N+1 becomes 2, and we're going to see a doublet. And you can think of it as a literal split to the simple triangular peak, and that's why we end up with the doublet peak. And then if N is 2, then we're going to see a triplet, because that peak is going to split twice. And if N is 3, we're going to get our quartet. And if anything greater than 3 is present, that's when we would see the multiplet, because 4 plus 1 is going to give us our 5, or anything greater. A good way to think about this is if you imagine you had a piece of paper and you cut it once, you're going to end up with 2 pieces. So one hydrogen will split a peak once, And that's going to result in 2 peaks, in fact, or 2 mini peaks. And so for each hydrogen, we get a split, and each time that peak is split, we get n+1 mini peaks. This splitting only occurs for hydrogen atoms on carbon atoms, and it is only split by hydrogen atoms on other carbon atoms. And so, for instance, hydrogens attached to, say, oxygen in an alcohol or nitrogen in an amine, they don't get split by other hydrogen atoms, neither do they cause splitting. And so any alcohol hydrogen will always appear as a singlet, as will any hydrogens present on a nitrogen atom. And so if we look at an example of propanoic acid that I'm showing here, we know that there will be 3 peaks because there are 3 different environments for the hydrogen. There are 3 sets of non-equivalent hydrogen. And we also know that they will be present in a ratio of 3 to 2 to 1. In other words, the methyl peak will be 3 times larger than the alcohol peak, and the CH2 peak will be twice as big as the OH peak. But what we know now is that when we zoom in on those peaks, they won't actually all look like simple triangles like I've drawn at first. The OH peak actually will, of course, because that doesn't get split. But the CH3 peak, that size 3, that's the biggest peak, that will get split by the 2 hydrogen atoms on the adjacent CH2. And so instead of it being one big singlet, it's actually going to be a triplet because it's been split twice. And similarly, the peak caused by those 2 hydrogen in the middle have got 3 hydrogens on the neighbouring methyl group, and so that means that the CH2 peak is going to be split 3 times, and we would actually see a quartet for that peak. The next example that I want to take a look at is methyl propanoate, an ester. You can see the ester group in the middle here. Now, if we take a look at this, we can see that there are 3 sets of non-equivalent hydrogen environments. We have to be careful here because this methyl group and this methyl group, you could be forgiven for thinking they were the same thing because they're both methyl groups. But the methyl group on the right-hand side is next to this highly electronegative oxygen, whereas the one on the left is next to this CH2. So they're going to have dramatically different environments and therefore appear as separate peaks. So there are going to be 3 peaks. The peak on the left is going to have an integration value of 3 because there's 3 hydrogen atoms causing it. The next one, that will be a size 2 peak because there's 2 hydrogen atoms causing it. And the one on the right will be 3 as well because there are 3 hydrogens causing this peak. So 3 to 2 to 3. Now, when we take a look at the splitting pattern, we're going to get 3 different types of peak. Starting with the easiest one, the methyl group on the right-hand side is attached to an oxygen. So because it isn't even attached to a carbon, this is not going to have any splitting at all, so this will be a singlet. And then if we approach the carbon atom over here, the CH2 group, there are no hydrogen atoms on this carbon atom, and there are 3 hydrogen atoms on the adjacent carbon atom here. And so that means that N is equal to 3, N+1 is 4, so this will appear as a quartet. From the point of view of the methyl group on the left-hand side, there are 2 hydrogen atoms on this CH2 group, so that means N is 2. The peak is going to split twice, and so N+1 is 3, so this will appear as a triplet. So we will have 3 peaks, a size 3 triplet, a size 2 quartet, and a size 3 singlet. This is definitely a characteristic cluster of peaks that you can expect to encounter, and you can make a quick judgment if you are well practiced with this. So a triplet next to a quartet tells you that you have got a CH3 group next to a CH2, because that is the most common grouping of atoms that gives rise to a triplet and a quartet. We've got a very complicated looking example for number 3 here, and if we take a look at this at face value, it looks confusing as to how many peaks we're going to have, because we've got 2 methyl groups, 1 on each end, and we've got 2 CH2 groups in the middle. So we could think that there were only 2 peaks. but actually there are no equivalent environments here because the CH3 on the left-hand side is next to an oxygen, whereas the CH3 on the right-hand side is connected to a carbonyl group. And in the same way, the left-hand CH2 group is next to that oxygen, whereas the right-hand CH2 group is next to the carbonyl. So there are no equivalent environments here, which means we will see 4 peaks. And these will be present in a ratio of 3 to 2 to 2 to 3 because of the number of hydrogen atoms in each environment. When we look at the splitting pattern, the CH3 on the left is next to an oxygen, and so that won't split, and so that will be a singlet. The CH3 on the right-hand side is attached to a carbon, but there's no hydrogen atoms on it, and so that won't split either, and so that will be a singlet as well. The CH2s in the middle, neither of them are on the outside next to anything that contains any hydrogen, so we've got the oxygen and the carbonyl group, and so they're just next to each other. And so from the point of view of both of them, there are 2 hydrogen atoms on the neighbouring carbon atom, and so that means that this CH2 on the left-hand side will be split twice by the CH2 on the right. So N is 2, N plus 1 is 3, and so this will be a triplet. And in the exact same calculation, the CH2 on the right will be split twice by the CH2 on the left, and so that will also become a triplet. And so having 2 triplets, and certainly when there are no quartets on display, that is a really surefire sign that you've got 2 adjacent CH2 groups, because that is by far the most common way that you can get 2 triplets. And so that will save you time in a test if you see 2 triplets and you think, right, that's probably CH2, CH2 connected together in one sort of piece of the puzzle. The last example that I want to look at the splitting pattern for is butane. Now, since butane is a hydrocarbon, it looks like it should be easy, but there is a misconception that is really common that I want to highlight and help you to avoid. First of all, this molecule is symmetrical down the middle here, and as a result of this line of symmetry, there will actually only be 2 peaks, one for the CH2 groups and one for the methyl groups that there are at the end. Now, secondly, these 2 peaks are going to have an integration value of 6 to 4, because there's 6 hydrogens in a CH3 environment and 2 in a CH2 environment on each of those positions. So 6 to 4, that is going to simplify down to 3 to 2. The complication comes with the splitting pattern. The n plus 1 rule states that a particular peak, so let's take the CH3 peak, it will be split by the number of non-equivalent protons on adjacent carbon atoms. And so from the point of view of this methyl group, there are 2 protons here, and from this methyl group, there are 2 protons here. But the important thing to remember is that this molecule is symmetrical, so we can in fact just focus on one half of the molecule. So for the CH3 peak, there are 2 hydrogens on this CH2 group, and so this peak will be split twice, and so it will be a triplet. It will be a size 3 triplet. And so the important part there is that because there is a CH2 adjacent to this, that will split the peak. The CH2 adjacent to the other one is saying that this peak will be split in the same way, and so it will be a triplet. The most confusing part is in the middle here, because if you're not careful, you'll think of this CH2 as being next to 3 hydrogen atoms on the left, on this carbon, and this carbon has got 2 hydrogen atoms on the right. So you could easily think that N was 5, N plus 1 was 6, and this will be a multiplet. This is not the case. It would in fact be a quartet. And the reason is that these 2 CH2s are the same environment, so they will not split each other. They are causing the same peak, so they will not interact with each other in a way that will affect their spectrum. And so for all intents and purposes, we can pretend that one half of the molecule just isn't there, because one thing will not split itself. And so that means from the point of view of the CH2, the only neighbouring hydrogens are on this carbon atom, and there are 3 of them. So N is equal to 3, N plus 1 is 4, so we will have our quartet. So the CH3 will be a triplet, the CH2 will be a quartet, and then we've hit the identical environment and another identical environment. So 2 peaks, a ratio of 3 to 2, and that will be a triplet and a quartet, respectively. Okay, that's the end of this video. I hope it was useful. I'll see you again soon.